In this video, we're going to be talking about how we can use our knowledge of triangle similarity to prove some other things. I'm not even going to read through the list right now because it might be word jumble and just confuse us, so let's just get into what we're going to actually be doing. So recall that this definition of similarity is super important. As all definitions are in geometry, you need to make sure that you understand what comes from two triangles being similar, right? So we know that if two triangles are similar, we know two very important things. We know that their corresponding angle measures are congruent, and we also know that corresponding sides are proportional. So you need to understand, you need to know this like the back of your hand. So here's a way that we can use that. So it says the two triangles below are similar. What are some conclusions that we can make? Well, these conclusions are going to come exactly from that definition that we just spoke about. First thing that we talked about was all corresponding angles are congruent. Which angles? Well, we got to see which ones are corresponding. So some conclusions that we can make, we can say, hey, angle P is congruent to angle S. We know that, right? If we know that our two triangles are similar, the question told us that, I can make that conclusion. We also know, or can conclude, that angle R is congruent to angle U. And again, that comes straight from the definition of similarity. Last but not least, you probably guessed it, we can say that angle Q is congruent to angle T. And again, this comes straight from the definition of similarity. So that's the first part, dealing with our corresponding angles being congruent. The second part of the definition talked about proportional sides. And remember, when we had our proportional sides, this was when we were making our fractions and proportions, right? So for example, we know that PR, right, which is this side here, we know that PR over SU is going to be equal to, let's say, so we did PR over SU is going to be equal to, let me pick one other pair of sides, let's just say PQ over ST, right? We know that that's going to be true. And again, that comes straight from the definition of similarity. We can make those proportions. We also know, let's say I took PQ and ST again. If we did PQ over ST, I know that's also going to be equal to, if we did RQ over UT, right? So I can make these proportions here just from the definition of similarity. Now there's one that I missed. You can also do PR over SU equals, and we didn't do this one yet, equals RQ over UT, right? We know this. We know how to, typically what we see though, we usually put them all next to each other like this, right? So yes, all three of these proportions are going to be congruent, but I also wanted to show you guys that we can separate them and just use two, right? So just doing the green and the yellow, and then just doing the yellow and the purple, right? Like those are also proportions that we can take. We can break up those three fractions and make these other types of equations as well, just from the definition of similarity. So a similarity proof that we are used to, right? We're used to seeing an example like this. Now, here are the steps if we were going to make that proof, right? We obviously address that our lines are parallel, which I didn't label. You want to make sure we label those. So we've mentioned vertical angles here, right? So we have ACB and DCE. And then we used our alternate interior angle theorem to say that angle B is congruent to angle D. And then we've used angle similarity to prove that our two triangles are congruent. Now, we're used to seeing these types of proofs already, but now we're going to go a couple of steps further. So again, what I need you guys to be able to connect, right, is what we did on the last slide to what we're doing now. So in the last slide, we were given that two triangles are similar, and we were able to make a bunch of conclusions. Here, we weren't given that the triangles were similar. Hey, but guess what? We have now concluded that using our geometric logic. So guess what? Now I know these two triangles are similar. I can make all of the conclusions using that definition. Now, this brings me back to thinking about like triangle congruence and CP/CTC, because it's the same idea, right? Once you have similarity, you're able to make so many conclusions just using that definition. Now, it depends on the question you're working with. The question is not going to tell you to make all 6 conclusions, but we got to make sure we recognize what our new statements or what our new proof statements are going to be. So these are some new things that you guys might see. Now, instead of, it's not going to tell you to prove triangle similarity anymore, but two new things you will see, you might see these proportions created, right? It might say, hey, prove this. Now, what you need to recognize is that these are proportions of corresponding sides. Because people see a lot of fractions and they freak out, but guess what? If you know that your two triangles are similar, we're already used to making these proportions. So if you see these fractions written out, you need to recognize the fact that these are going to be the proportions of corresponding sides, right? So we first need similarity. Now this is a completely new one that we've never seen before. But what you need to see is going from this step to this step. So going down, I'll do a different color. Going from what we did up there of making our proportions to this step, all we are doing is cross multiplying. So mn times mr equals mq times mp, right? So if the question is asking you to prove something like this, you need to go backwards and you're going to say something like this first. Before this, right, this is like a flow chart. Before this, we always need similarity first. If you have proof statements like this, like one of these two, and you do not prove similarity first, you're going to be already wrong. So let's just get into an example. So with the exact same proof that we had in the last slide, instead of proving similarity, it's asking us to prove that AC over EC equals BC over DC. Now again, we need to recognize that, hey, these are proportions of corresponding sides. So I know I need to first prove, and what I like to do too is I'll highlight those, and these two triangles are not drawn in the same orientation, so let's do that. So this is going to be CDE. I'm going to decide to keep this orientation the same, and then I will switch triangle ABC out. So my single arc needs to go in the top. That is letter C. My double arc needs to go in the bottom left. That is going to be letter B, and then we have A. So again, what this is asking us to do is it's saying, hey, we want to prove that AC over EC is equal to BC over DC, right? Once we have similarity though, we can already say that, right? Again, these are just proportions of corresponding sides. So once we have our similarity, I can go ahead and say, hey, AC over EC equals BC over DC. We know that from the definition of similarity, like that's a given. But now we need to know what this new reason is going to be. The reason, and you guys need to make sure you know this, is corresponding sides of similar triangles are proportional. Make sure you know that, right? So for this proof, right, it looks very complicated, but if you analyze that, it's just a proportion of corresponding sides. We already have that from the definition. So proofs like this, where you have proportions created, is just one extra step after you prove similarity. So this is one extra step. Now you can probably guess that the next slide is going to be the other proof statement that we are exposed to. The other proof statement, again, we got to work backwards from something like this, though, because if you're given something like this, yes, we've just done the previous example, but you got to kind of try to figure out which sides that you are working with. Again, I like to highlight them. So if our two triangles were drawn separately, we have DCE and we have CBA, right? So I'll always highlight. So we have AC, DC. Oh, I must have drawn something wrong here. Double check that. So we have D, CE, and then we have B, C, A. Oh no, I think I drew it right. Okay, whatever. So, oh, we did. All right, never mind. So we want to make sure we draw them in the separate orientation, and then we highlight the sides that this is talking about. So we have AC, we have DC, and then we have BC, and we have EC. Now, it wasn't matching up at first because it's not really supposed to, but once you highlight your corresponding pieces, you can kind of figure out the proportion that you're going to be making, right? If you see a diagram that looks like this, and you know you're dealing with these four sides, you guys already know how to make your proportions, right? Just from this, I know my proportion. If I'm starting with AC, I know my proportion is going to be AC over EC, right? AC over EC equals BC over DC, right? Now, what you should notice is that when you draw your diagram and highlight, if you have this proportion, you want to double check that when you cross multiply, you're resulted with this, right? So again, we're working backwards. We look at what we're trying to prove, right? We know that before this, we need a proportion. So in order to figure out what the proportion is, you have your triangles drawn separately, you highlight the pieces, and then you make your proportion based on your knowledge of triangle similarity. So our fifth step is writing that proportion in. AC over EC equals BC over DC. Our reason is exactly what we said on the last slide. In similar triangles, corresponding sides are proportional. So I'm not going to write it. You guys can go back, rewind to the last slide because it'll take me a while. But then your sixth thing, right? Again, we said if we cross multiply and we do that, we're going to get AC times DC, which is what we want from here, right? We want to make sure it aligns, equals BC times EC. Right? And again, we want to make sure that it aligns. So we're good here. Now this is a new reason. Now this reason, it's a little weird, it's a lot of word jumble, but we need to make sure that we are writing it correctly so we guarantee our points. This reason is, it's the products of the means equals the product of the extremes. And again, it's a lot of word jumble, but you need to make sure you are writing this entire thing out. So again, with all of these proofs, what you need to do is just look at what you're trying to prove and work backwards. Note that all of these proofs, all these extra steps that we added, all rooted with we first needed similarity, right? Now a proof like this where you have products is 2 extra steps. Now first you needed that proportion, right? Working backwards, we needed the proportion, and before that we needed similarity, right? So just to wrap everything up for us, our new reasons to justify statements like this, if you have a proof statement that involves proportions, your reason is always going to be in similar triangles, corresponding sides are proportional. And then if you have something like this, if you're making a statement like this in your proof, your reason is the products of the means equals the products of extremes. You need to write this whole thing to guarantee your point.